Hey everyone, so today I'll be talking about my Physics Lab 5, so let's get started. Okay, so for the intro, the purpose of this lab is to observe the motion of a system in equilibrium. And as you guys know from our previous test, when doing problems in equilibrium, we will always make the system or the forces all cancel out with each other, aka making F net equals 0. And this means that the velocity is constant and acceleration will be 0. And we will try to predict acceleration, which we predict will be 0, but we will predict it in the glow script and tracker. And here's just a preview of the main results. Now, as you can see on the two graphs, this is like a velocity graph, just to keep in mind. So as you can see, there is no slope. That means acceleration is equal to 0, and you guys can probably guess that it's from the computational model. Okay, so some physics principles in greater detail. Like I said before, F net will equal to 0, so that means the x components, y components, and z components of forces will equal to 0 and all cancel out. And some assumptions we'll have to make is that the object is moving on a frictionless surface. Okay, so here is just a brief, cute little drawing, and I will show you guys a free body diagram of what I am trying to replicate, or pull F tension on the mass. And then I like to do coordinates because it's just easy to visualize. And then we will not forget F graph from the Earth, and then the x and y components of F graph, and then finally the contact force from the ramp, or I guess normal force. And just to keep in mind, these are all not to scale, but it's just a quick overview, a quick brief diagram of what we're going to be seeing. Okay, so detail of the experiment, like I said before, here's just what was going on. So here's the book, which is the ramp, my eye contacts case, and a string of floss. And the angle between those is 45 degrees or somewhere around there. The mass of the eye contacts case was about 0.02 kilograms, I believe. And then constants that we will be working with is the gravitational constant, which is negative 9.8. And here's the graph from the experiment that we were able to get. It's almost constant. As you can see, there's like a slight curve right here and just bumps all over, mostly because, like I said before, it is not frictionless, but we will have to assume that it is frictionless. And then just here's another close-up of the experiment. Okay, so details of coding. So some initial conditions we had to put was the same as the initial conditions from the experiment. And then down below are some of the coding that we used in order to model our data. Now over here is just not a good picture, but I just have the graph for the computational model on the corner right there, but I kind of cropped it really badly. But you can see that it's very linear slope, very constant, and I believe this shows the position over time, so it shows that velocity is very constant. And yeah, so we will predict velocity, and we will, or not predict velocity, sorry, we will predict acceleration. I will not write that, but yeah. Okay, so some similarities and differences between the two. In real life, the observed model, as you can see, there's a big outlier right there. It's generally increasing, but there are slight bumps. So as you can see, this is a graph showing velocity, and it is not constant. But when you see this graph, which is the computational model, it is very constant. It's basically a straight line. It goes for a value of whatever that value is, 4.5 something, and it's just straight throughout. So it just shows how these two have very different results, because like I said before, there are sources of error in the real life experiment with the friction and other forces and external forces that we might have not accounted for, because we're in a more simplified physics class. And then here's just a graph of the position basis time graph that I was able to model for the actual experiment. And yeah, I just changed it to velocity so we can get a better look at it. Okay, so what does it mean? If we were to add in a z component into the system, would that change F net? No, it would not. It would still be 0. And then what would the results mean in terms of predicting the velocity of systems in dynamic equilibrium? The physics we are learning is heavily simplified.